Okay, we have two sections left in Chapter 6, 10 and 11. 10, which we'll talk about today, we're going to be discussing how to put all of the information we've been doing this chapter together and what it means in the graph. Okay, and then section 11 is actually using a graphing calculator to find some of these points that were at like maximum, minimum, those kinds of things that we'll talk about today. There's no web work for section 11, there's just web work for section 10. So in addition to section 11, we're going to be kind of doing a project in class on using a real world problem and how we would solve it using polynomials. Okay, so section 10, there's a few important things that you need to know about a graph of a polynomial. Okay, and to start with, there's something called end behavior. Anyone want to take a guess as to what end behavior might be when it comes to looking at a graph of a polynomial?
Ending result.
Okay, ending result. There's one stab at it. End behavior. Any ideas? No? Okay. If you guys want to turn your computers around or something, just so I know you're...
It says the graph approaches positive infinity or negative infinity.
Okay. So, there are lots of different polynomials. Maybe this is one. Okay. This one actually goes through the x-axis 1, 2, 3, 4, 5, 6, 7 times. The end behavior is what happens when it doesn't turn anymore. It just takes off and goes forever in one direction. That's the end behavior. Okay? So I would describe this end behavior as x goes to infinity, as x is getting bigger and bigger and bigger and bigger and bigger to the right. We call that positive infinity. It's going positive to the right forever. Okay? Y on this end behavior is going up forever, which is also positive infinity. Okay? So as x approaches infinity, positive infinity, y approaches positive infinity. So someone describe the end behavior on the left side. As x approaches 1, negative infinity, y is going down forever, negative infinity. Okay, that's end behavior. What about end behavior of the line y equals x? What does that line look like? Y equals x, what does that line look like? This is like algebra 1. Y equals x, what does that line look like? It's a line. What's the y-intercept? 0. What's the slope? 1. Y-intercept 0, slope is 1. Y equals x. What's the end behavior of this line? As x goes to positive infinity, y goes where?
Negative.
Positive infinity. As x goes to the negative infinity, y goes negative infinity. That's the end behavior. Okay? What about y equals x cubed? 0, 0 is a point on it. 1, 3, 1, 1, right? 2, if x is 2, y is 8. Okay? Negative 1, and then 2, 8. 2, 4, 6, 8. So there's y equals x cubed. What's its end behavior? Yeah, x goes to positive infinity, y goes to positive infinity, x goes to negative infinity, y goes to negative infinity. So the end behavior is the same for this graph and this graph. right? How many solutions are there to this problem? Y equals x cubed. How many zeros? How many should there be? What's the degree? 3. So there should be 3 zeros. How many are there? 1. So that tells us there are 2 imaginary zeros. 2 imaginary. Okay? Notice that y equals x goes straight through. If there's 2 imaginary, there's kind of a kink in the graph. Okay? End behavior is going to always be the same as these two if the degree is odd. Okay? If the degree is odd, end behavior looks like this. As x goes to infinity, y goes to positive infinity, y goes to positive infinity. As x goes to negative infinity, y goes to negative infinity. Will always be that for odd degrees. What's the degree of this? 1. What's the degree of this? 3. So if it's a 5th, a 7th, a 9th, an 11th, a 13th, whatever the degree is, if it's odd, the end behavior will always be the same as these two graphs. Okay? Now, let's talk about y equals x squared. What does that graph look like? What shape? This is the last chapter. It shouldn't be that difficult. It's not a V. V is absolute value. It's a U. A V actually goes to a point at a vertex. That's not a U. It's a U. It's a U, and it goes through, what, 2, 4, something like that. What's the end behavior of that? As x goes to positive infinity, y goes to positive infinity. As x goes to negative infinity, y goes to positive infinity. Every even-numbered degree polynomial will have this end behavior. Okay? Every odd will have this end behavior. Every even will have this end behavior. So if it's an x to the 4th, a 6th, an 8th, a 10th, it will always end going up. Now if I put a negative in front of this, what happens to the graph? It flips over the x-axis and it goes down. So what's the end behavior now? As x goes to positive infinity, y goes to negative infinity. As x goes to negative infinity, y goes to negative infinity. It flips down. Same thing would be true if I make this a negative. My graph is now opposite. So as x goes to positive infinity, y goes to negative. As x goes to negative, y goes to positive. Same is true here. When I flip it negative, that's what happens. And it just changes exactly opposite of what you had for end behavior. Okay, so for odd end behavior, it looks like this. Even looks like this. If it's negative in front of an even, looks like this. If it's a negative in front of the odd, looks like this. Okay? Now, there's other things with graphs that you need to understand vocabulary-wise. And they are called increasing and decreasing parts of the graph. And it's typically around something called critical points. Critical points are zeros, where it crosses the x-axis, maximum and minimums. So as an example, let's say I have the graph that does something like this. Okay. Critical points are going to be the zeros and the maximum and minimums. This is a maximum, local maximum. This is a local minimum. And the reason we call it local, does this graph have an absolute maximum? Look at the arrow that goes up forever. It goes to infinity, which is not an absolute maximum. It's going to go on forever, never stopping. So it doesn't have an absolute maximum, but it has a local. Within this window, there's a maximum right there. So it's called a local maximum. Okay, within this window, there's a minimum right here, but this graph has no absolute minimum because it goes down forever. never going to stop. Okay, so these are critical points. And when we identify critical points, particularly the maximum and minimum, we can talk about whether this graph is increasing or decreasing. Okay, we always read a graph from left to right. So if I start at the left of this graph, which is at negative infinity, and I'm moving right along the x-axis up to this first critical point, is this function increasing or decreasing? Are the y values getting bigger or smaller? Yes. So this is an increasing function to here. Then it decreases to here. Then it increases forever. Okay? So if we ever are asked, where is the function increasing, where is the function decreasing, that's what they're looking for. From the maximum down, it's decreasing. So I would write where it's increasing from negative infinity to whatever this point is, 1, 2, 3, 4. It's increasing. Actually, we don't include 4 because at negative 4, it's nothing. It's just flat. Okay, it's decreasing from negative 4, this is increasing, from negative 4 to 3 on the x, right? It's negative 4 here to 3. That's where it's decreasing. And then it shoots off and increases again from 3 to infinity. I can do a union, 3 to infinity. Does that make sense? Talking about increasing and decreasing. Okay. Maximum and minimums, if you're ever asked for maximum and minimum on WebWork, it's the y value. It's the y value. So the maximum value here looks like 1, 2, 3, 4, 5.5-ish, somewhere in there. The minimum value looks like 1, 2, 3, 4, negative 4. But when you're talking about where functions are increasing or decreasing, you're dealing with the domain intervals, the x values, not the y. Okay, so let's put this to play here. Let me find where's my Algebra 2 book go? Okay, so let's talk about drawing functions given certain information. Draw the graph of a cubic function with solutions negative 6 and a repeated root at 1. Negative 6, repeated root at 1. Cubic, what does cubic mean? What's the degree of a cubic? 3. Okay, if it's a 3, what's the end behavior going to be? Like this. Right? Okay, so I know the end behavior. What do the roots tell me? What is the negative 6 and repeated root of 1? What does that mean on a graph? Those are the solutions. That's what I solved for, and that's what I got. I got negative 6 and a repeated root at 1. What does that tell me? What are the solutions of a polynomial tell me? What does the root tell me on a polynomial function? When I go through all the synthetic division or long division, I get the solutions. What does that tell me? Yes, and what do the zeros tell me? What does that mean? X values where? It's the x-intercept, where it crosses the x-axis. Roots, zeros, solutions. We've talked about this over and over with quadratics. When you solve it, what you're getting are the x-intercepts, the roots. Okay? So if they tell me the roots are -6 and repeated at 1, 1, 2, 3, 4, 5, 6, this function goes through -6. What does it tell me if it's repeated? What does that mean? How do I get a repeated root of 1? So I have a function like this. It's 1 twice. What does that mean if it's a root that's repeated? What happens on the graph?
It goes up and then it goes down.
It bounces. It bounces at 1. Okay? So I know the graph's going to go through this point, and it's going to bounce at this point, and the overall end behavior is going to look like this. So from this 0, it's got to go down, right? And from this 0, it's got to go up. So between, and it's got to bounce, it's going to have some behavior that looks like that. It allows me to sketch the graph if I know what end behavior is, and I understand that it's what degree it goes with. If it's an odd degree, end behavior looks like up on the right, down on the left. If it's even, they're both up. The roots tell me exactly where the graph's going through the y-axis or the x-axis. If it's repeated, it's going to bounce. The only thing that I really can't get without calculus is what this value is, what the maximum, the local maximum is. Okay, so tomorrow we're going to talk about how to find that on a calculator, graphing calculator. For now, when you're asked to sketch it, all you know is the maximum occurs somewhere in this area, but you don't know exactly where. That's why it's called a sketch and not a precise graph. Okay, it could be, I could have gone up all the way, I could have gone like this. We don't know what the height of that maximum curve is without just trial and error. Okay, we can't do that without a graphing calculator. I can do it with calculus, but you guys can't do it yet. So that's where we're going to learn graphing calculators and how to find those. But knowing what we've just gone over will allow you to sketch graphs with certain information. Okay, let's try another sketch. Let's do, which one do I want? Here's one that's got roots of -4, -3, 1/2, and 3, and has an absolute maximum at 2, 5. Absolute maximum, not local. So if it has this many zeros, what kind of function is it? What's the degree? The minimum. Minimum degree. What's that? Squared would have 2 solutions.
So it's
Fourth degree. Is that even or odd?
Even.
Even. It didn't tell me whether it was negative, so we're just going to assume positive. So what's the end behavior going to look like? Even goes like this. Even goes like this. Odd is like this. Even is like this, like a parabola, because parabolas are even. Okay? So I know the end behavior. And I know my zeros. -4, -3, 1/2, and +3. I know ultimately this is going to shoot off up because the end behavior is it's a fourth. That's going to go up. I also know I've got a local maximum at 2, 5. So I'm going to have something that shoots like this, right? I almost feel like I'm going to have a repeated root to hit that maximum. Because if it doesn't, if my maximum's up here and this were to come back down and come up, there's no way I could get that maximum, right? So there's probably a repeated root in here. Or the end behavior could be, this could be a negative. If it's a negative, and I have a maximum here, it could shoot down and down. 2, 5 is here, so it could come down. I don't know where this minimum is or this maximum, but it could look something like that. Okay? Just knowing the degree and knowing your zeros is going to give you enough information to be able to sketch graphs. On web work, you're going to have to, I think there's a lot of matching, like pick the graph that matches this given information, that kind of thing. How would you graph 8x cubed plus 10x plus 6? How would I start this? Yep, it's going to be like that. How could I, if I'm not given any zeros, how could I figure out some? Yep. My possibles are plus or minus 1, 2, 3, and 6. Right? I want to make sure I get one that's actually got zeros that are integers. So I'm going to pick a different one just to illustrate this. But if I do, let's do this one. Plus 9x minus 27. And I want to graph this. My possibles, plus or minus 9, not 2. And then divided by, okay, so I have possibles plus or minus 1, 3, 9, 27, 1 half, 3 halves, 9 halves, 27 halves. For the sake of time, I'm not going to list them all. Okay, so let's just try 1. Two, negative 4, negative 4, 5. That's not going to work. Negative 1, negative 2, negative 8, 8, 17. Nope. Let's try 3. 2, 6, 0, 0, 9, 27. There it is. So what do I have left? 2x squared plus 9, right? If I solve for this, 2x squared equals negative 9, right? X squared equals negative 9 halves. Square root of that is an imaginary number. So I only have one real solution. Okay? And I know the end behavior is going to be like this. So I know my one real is that x equals 3. And it goes through negative 27. Let's just go by threes. 3, 6, 9, 8, or 12, 15, 18. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's going to go through there, the y-intercept, right? One thing I want to show you is when you have imaginary solutions, you can tell from looking at the graph, and it's interesting. Look at this graph here. Do you see how from the maximum to the minimum, it's not a smooth line? It kind of has a little kink in it. Okay? It looks like this is a cubic because it only goes through the x-axis 3 times. Whenever you see kind of a bend in the graph, you know there's 2 imaginary solutions. Okay? So yes, it's got 3 zeros, but it's going to have 2 more. This is actually a 5th degree function because of that little kink that you see in between. Okay? Whereas this one is just a cubic function. There's no strange kink in it. So if I were to graph the one we just did, I know it has 2 imaginary solutions. I'm curious to see what it's going to look like in the graph. And I'm going to take my book over so I can actually graph it. And it is 2x cubed minus 6x squared plus 9x minus 27. Oh, I did turn it. Okay, so we figured out it went through 3. Does the end behavior match with what we thought it should? It goes up to the right and down to the left because it's a cubic. Yep. Does the y-intercept happen at negative 27?
Yes.
Yes. Do you see the bend?
Yeah.
Okay. So that, from looking at it, I know there's 2 imaginary solutions. Okay, so it's only going to go through once, even though it's a cubic. A lot of times cubics will go through, have a maximum and a minimum. This one doesn't have that. It's just going right through 3, hits the y-intercept, and has that little bend in it, which tells me there's 2 imaginary solutions. Let's do one more with a 4th. X to the 4th plus x cubed minus 12x squared minus 10x plus 20. Okay, possibles here. Okay, I don't have to divide by anything, which is nice. 1, 1, negative 12, negative 10, 20. No placeholders needed. I'm just going to try 1. Nice. Found the first one. But this is an x to the 4th, so I have to do it twice, right, to find all of them. Let's try 1 again for the fun of it. Just see. 1, 1, 3, 3. That's not going to work. Let's try negative 1. 1, negative 1, 1, negative 1, negative 11. Nope. Let's try 2. 1, 2, 4, 8, negative 2. Nope. What's a way I could just save myself all of this heartache here? Yeah. 1, negative 2, 0, 0, negative 10, 20, and there it is. So I found 1 and negative 2 are my 2 zeros. Then I have x squared minus 10 equals 0, right? So x is equal to plus or minus the square root of 10. So I have 4 real solutions, which is nice. 2 of them are irrational. 2 of them are rational, but that's okay. So if I come over here, I have 1, negative 2. What am I doing? I have 1 and negative 2. Anybody know what the square root of 10 is off the top of your head? Someone have a calculator? It's going to be somewhere between 3 and 4, closer to 3. 3.16. 3.16 and negative 3.16. So those are my 4 intercepts. What's the end behavior going to be? It's an x to the 4th. It's going to go up at the ends. Okay, so I know from here it's going to shoot up. From here it's going to shoot up. What is my y-intercept?
1 and negative 2. Wait, no.
What's my y-intercept?
Um,
How do you find the y-intercept?
Negative 0.
Okay, what's the y-intercept?
10, 20.
20.
Oh.
20. So I'm going to go up by 2s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? I don't really know what's going to happen between here, how far it's going to go. But it's going to have something like that as its general shape. Okay? Because I know the end behavior and I know my zeros. So let's graph it and see how close we were. X to the 4th plus x cubed minus 12x squared minus 10x plus 20. So that's what it looks like.
Pretty close.
Yep. The only thing is I made the two bottoms about the same minimum, but they're not. They're different minimums. But I wouldn't know what the minimums are without graphing it. So when I'm asked to sketch it, where's my graph? That's what I got.
Yeah.
When I graphed it, that's what it actually is. So it's close. It's a sketch. Okay? All right.